Okay, crystalline. I mean, these are pretty simple, right? Don't make more out of it than it needs to be. So what should you write? How about organized and not organized? One has to be organized and one cannot be organized. One has to be completely randomized, like Legos in a box, not connected together, and Legos in a box, all of them connected together. Okay, how about this one about impurities not necessarily being a bad thing? I don't like that word. Okay, it can make it more rigid. How about ridge? Not necessarily.
Depends on what you want it for.
Yeah, there you are.
Do you like brittle potato chips or chewy potato chips? What else? What? Okay. Yep. What else? Sure. You could just do just like a general. I don't know, melding. Depending on what the situation is, I mean, all you're doing is this metal has these properties, this metal has these properties. When I mix them together, this new thing has properties of both of them. So it could be like brass. What's the real reason do people do brass?
Stronger than copper
No,
or less valuable?
no. I mean, yes, but that's not, nobody cares about that.
No, it's
Not, it's less anti than copper. It's pretty, period. Stop talking. That's the end of it. I didn't hear if that's what you said, but it looks like gold, right? There isn't any other reason really to do it. I mean, I guess there are several reasons to do it, but for the most part, it's because it's more attractive. But there are lots of right. No, other way around.
Or cut into the copper sword with a bronze sword.
Is that what you said?
Yeah.
You sure?
I do that stuff all the time, so it's totally possible.
So did you guys find this one?
I found multiple different things, like homogenized makes it stronger.
What did you guys come up with?
Just
What?
It makes it stronger.
Yeah, again, don't like that word.
So it makes it.
folding in impurities and layering the different like concentrations of those impurities, like you said, Damascus steel.
Sure. So what this does is it improves the what? What do you want to say?
Rigidity.
But don't you want? I guess.
Which has higher tensile strength, steel by itself? You know?
But I heard if you like fold it enough, it becomes brittle.
Uh-huh.
That's definitely true.
So it'll increase rigidity without removing all the flexibility of the sword. And the important thing is you can only do it so many times because you're doing what you said is imparting impurities and imparting interstitial defects, which might put, because we had several versions of that, right? Holes and then substitutions and things like that. All of those are possible, and they happen when you beat this other substance into it. It also gives a layering effect to it, but the layering effect is like these bricks in this, sorry, those bricks back there, they're not lined up, right? Why not?
Because it would make it more like.
Because it could cause shifting, right? So it's like every other one sticking together, so it doesn't allow this to laterally shift. Same thing with the sword layering. The layers aren't right on top, aren't flat against each other. They're offset, so they increase the strength, increase the rigidity, and still impart some flexibility. But if you do it too much, then you impart too much rigidity, and you get onto brittleness. Another one of these like movies are stupid, like when they do stupid science stuff. 80s movie, Highlander. There's a part in the movie where this woman is like, the sword was folded over 200 times. I'm like, that's, no, it's not normal. If you hit that against a wall, it would shatter. Like it would have the rigidity of glass. It wouldn't have any flexibility at all. Like nobody would do that. So this is all in the blacksmith figuring out exactly what the right amount of folding is. And again, that's what it is. The sword, he makes a sword and then he beats the sword flat and then he turns it on its side and folds it and then beats it into a sword shape again and keeps doing that over and over again to the correct number of times where he's happy with it or the person who's ordering it is happy with it. Okay, how about the phase diagram? Something, no, not that,
Has to go back.
not that. There we go. So solid, liquid, gas, pressure is over here, temperature is over here, and you should have like melt, freeze. You can use different words. Vaporization, condensation, sublimation, deposition, and then we also wanted, can't really see that, that one. The triple point, and then, I don't know, it'd probably be somewhere over here, be the critical point. Just make this longer. What's the weird thing about the triple point?
After that,
It's everything simultaneously.
Yeah, all 6 of these phase changes are all happening at the same time. And it doesn't seem possible, but it actually happens, yeah.
what do you have from solid to gas?
Solid into gas is sublimation. And the other gas into solid is deposition. And then the critical point is that temperature at which it doesn't matter how much you jack the pressure up, you still can't get it to liquefy. It's in a weird, like, gas particles are supposed to be individual particles. And at the critical point at high temperatures, like 3 of them or 5 of them stick together, but they won't actually liquefy. So it becomes it acts very weird. These things here are helpful in doing some stuff. So the sublimation one, do you guys know what we use that for? I mean humans.
Fluid preservation.
Yeah. So what happens? How does this work?
You freeze something at a really, really cold temperature so no ice crystals form, right? And then after that, you let the ice or the water vaporize off without turning into a liquid so it doesn't destroy the structure of the food.
So you want to dehydrate the food, but you don't want to heat the food to get the dehydration off because then it ruins the molecules. So if I have a substance and it's right here, this black dot, and it's everybody okay with me saying it's frozen? It's in a solid state. So then I drop the pressure, and now I'm over here. So what happened when I dropped the pressure and crossed that line? All the solid water turned into a gas and just floated off. And so now you've got dehydrated food without having to heat the food. So that's why like the REI foods that are like beef stroganoff and lasagna, when you put water in them, they're pretty good. They used to be really bad, and now we've done a really good job of this. They actually have a sublimation facility at FlavoPack. Is it FlavoPack? FlavoPack. You guys know what I'm talking about? Like brand of frozen vegetables, FlavoPack. The factory or the warehouse and processing facility is on I-5 between Wilsonville and Aurora. It's huge. It's like, I don't know, 3/4 of a mile long. And inside of there's a sublimation. That most of their stuff is just flat out frozen peas and stuff like that, carrots and things. But they have a sublimation thing in there, and it's cold. Is the best way to say it. It's very, very cold. This is on this end. This is how we can get rid of caffeine out of coffee. So we do this with carbon dioxide, and caffeine will be solubilized in supercritical carbon dioxide. And so you just get the beans and the carbon dioxide at supercritical temperature. Well, the carbon dioxide is at supercritical temperature, which is like that weird liquidy, not liquidy state, and you send it through the beans and it pulls the caffeine out, which is a zillion times better than the old way. Does anybody know how else you can pull the caffeine out of beans?
So just roasted to death?
No, roasting doesn't get rid of it. Dichloral ethane, a toxic chemical. So when you decaffeinated coffee like 20 plus years ago, actually probably even 10 plus years ago, there'd be some of that residual, but not very much, but still some. So people who drank a lot of decaf coffee would sometimes have weird things happen to them because they'd end up with, their body wasn't able to get rid of the dichloral ethane molecule. So it just kind of built up and did bad things to them. But it's no big deal anymore, right? As soon as you take the beans out of this pressure and temperature, the carbon dioxide turns into a gas and just floats off. So it's just gone, doesn't matter. Why would a person want to change the viscosity of the motor oil between seasons?
Because as the temperature increases.
Okay, so let's do that. Temp up. All right, go for it.
As the temperature increases, viscosity decreases, I believe.
Okay.
So you would need a heavier weight so that the oil would be efficient for the engine.
So summer, you do what?
You increase the weight.
Add higher viscosity oil. And then winter?
In winter, you have lower viscosity or lower weight oil.
Yeah, they don't say viscosity on the
What does weight mean? Like
viscosity.
$5.
It's just, I don't know. Honestly, I don't know why the oil industry just didn't call it viscosity and give it the viscosity number. They came up with another term. Maybe the word viscosity was more complicated and they wanted it to be. I'm not going to spell that right, am I? There you go. The easiest way to think about this is when it's, 10 degrees Fahrenheit outside, what's going to happen to that motor oil that's a little thick, like syrupy? It's going to get thicker. So now when you go to try to start your car's battery has to crank the oil that's very thick through it. And so it'll be very difficult for it to actually move that, and your battery might go dead before the car starts. It's super important with like a diesel, which is like my truck has 2 giant batteries in it instead of just 1 giant battery or 1 battery. And let me get rid of that. Right, the vapor pressures for ethane and ethanol. Okay, so what'd you guys have for ethane? No? Yes? Maybe?
It was a weird number. It wasn't like in that
I didn't call it that because there's just so much inconsistency.
Well, I don't care about the inconsistency as long as it's the same
540 PSI
same website. What does that say?
It said 540 PSIG at 70 degrees Fahrenheit, and that's all I could find. It didn't give it any practice.
What is that? PSIG. You're not the only person that wrote
LCA
that.
gauge, which is atmospheric. Yeah, that's just standard atmospheric pressure. Standard atmospheric pressure.
PSIA.
Yes, because PSIA is at like no outside pressure, just vacuum.
Okay, so it's 540
Which is PSI.
PSI, pounds per square inch. And then the other one, the ethanol one is, let me do this. 5? So it'd be about 6. It's about 6 PSI for the ethanol. So why a dramatic difference between these two? Yeah, so definitely because of the intermolecular forces. So the ethanol has what? And the ethane has just dispersion. So that's the temporary one, that's the weakest of the intermolecular forces, so it literally can't stick to each other very well, which is why it turns into a gas very easily. And the hydrogen bonding means they like to stick to each other. It's the strongest of the covalent molecule intermolecular forces. So although the ethanol definitely has a vapor pressure, and if you were to open up a container of alcohol, it would evaporate away, just even if it's just rubbing alcohol, which has a slightly lower or higher vapor pressure or lower vapor pressure than ethanol, it would definitely evaporate away. But ethane is a gas at room temp. There isn't anything for it to turn into. How do you think they do this if it's a liquid at room temp? They just have so much stuff in the container that it's some of it stays as a liquid. So this would be like your barbecue grill kind of situation, just a lot of liquid, and knowing that there's going to be some gas over the top of it. All right.